Hello friends, welcome back my YouTube channel MS Maths. In this video, we are going to discuss about the solution of partial differential equation by using Laplace transform. How can we solve the differential equation by using Laplace transform? And we have discussed about the topic ordinary differential equation. The video of that topic you can watch from our playlist. Now we are going to discuss about the partial differential equation solution by using Laplace transform. So first of all, we have some special conditions, and before going to start the solution, and I'm just telling about the what is the condition to solve the partial differential equation by Laplace transform. There is a condition, there is a criteria. Basically, if you have a range of the variable, like if I'm taking the variable x and t, like the range of one of the variable or both the variable should be 0 to infinite. So I am mentioning here there is a range. Okay, this is the function, and you should know about that thing. Like if the range of that function, like y is a function and y is depending on two variable. So basically x and t are independent variable and y is a dependent variable, because in partial derivative, we can see that the partial derivative like that dy by dou y by dou x, or dou y by dou x, and dou 2y by dou x dou y. Okay, like this partial derivative can be this form. Okay, so basically there are not y, t. So there are two independent variable. Like independent variable is that variable in which with respect to we are going to differentiate the thing, we are going to partially differentiate the thing, and y is depending x and also t. So basically, like one of the variable, one of the independent variable, or both of the independent variable should have range 0 to infinite. Then we can use the partial derivative condition, partial derivative by using the partial differentiation equation by using the Laplace transform. Now here is the standard form. If we have the Laplace, if you just calculate the thing, and steps, I'm just talking about the steps. So first of all, there is a step to solve the partial differential equation, taking the Laplace transform, both side. Okay, now if I'm taking the Laplace transform, there will be a term del y by del del y by del t, or I'm just talking, it is not del, it is dou. Okay, I'm just pronouncing this is dou y by dou t, dou 2y by dou t square. And the Laplace transform of this thing is this, and I will prove how is equals to this term. I will prove it. Okay, and second step is nothing but you will get a OD, you will get an ordinary differential equation. Like you can see this type of ordinary differential equation and solve that ordinary differential equation. Third thing is that taking inverse Laplace transform, and then you will get the solution of that partial differential equation. I will solve a question also in this video. Okay, now first of all, if you have the if you have a term like dou y by dou t, okay, and you just want to calculate the Laplace transform of this thing. Okay, this is the first case. So it is s y bar. Y bar is nothing but the Laplace transform of y. S y bar x x s. Okay, s is the parameter, because we are going to taking Laplace transform with respect to t, our function with respect to t. Okay, s y bar x s minus y bar x 0. So like in first case there is a s, in second case there is a 0. But how? Like by using the definition of Laplace transform is the 0 to infinite e to the power minus st, and ft is nothing but del y upon del t, and it is dt. This is the definition of Laplace transform. Now I am going to apply the Euler formula. I am taking this one and this second. So what is the formula? Formula is that put first outside e to the power minus st and integrate del y over del t with respect to dt. Okay, now minus integrate and differentiate first, that is minus e to the power minus st, and integrate del y over del t with respect to t, and integrate this whole thing, and the limit is 0 to infinite, or you can put it like here. Okay, 0 to infinite, we can put it here. Now e to the power minus st, it is nothing but y. Okay, it is nothing but y, partial derivative y, and it is nothing but y e to the power minus st yt, or the limit is 0 to e to the power 0 to infinite. Okay, I'm putting the limit here, minus this is the e to the power s minus s e to the power minus st. Okay, and it is also y, and it is the limit 0 to infinite. Now you can see here, if I'm putting the limit and also dt is here, okay, this dt is here. Now I'm putting the limit. If infinite I'm putting here, there will like this will be the 0, e to the power minus infinite, 1 upon e to the power infinite, 1 upon infinite is 0, and I'm putting 0 here, then it is a minus of y. Okay, if I'm putting 0 here, this is the plus of y. Okay, minus of y because lower limit. Okay, first term is 0 and second minus y, and it is nothing but y x t, y x 0. Okay, this is nothing but y x 0. Okay, y x 0, and the Laplace transform, I'm taking the Laplace transform, so it is nothing but y x 0. Okay, no problem. Now here is the thing, I can take common this thing as 0 to infinite e to the power minus st ft. This whole thing is nothing but y dt. Now this is the definition where the function is y. So basically the Laplace transform of del y over del t is equals to s, and this is the definition of Laplace transform. Then Laplace transform of y minus y x 0. Okay, here, so this is s, and Laplace transform of y is nothing but y bar x t minus y x 0. Okay, let me check this is y bar or not. Okay, here it is not y bar. Okay, there is a mistake here, this is not a y bar also. Let me check also this thing. Okay, there is not a y bar, there is a simple y. Okay, now clear. So this term will get like this. Okay, there is some problem, and I can like if we derive this for like the formula, then that is not a wrong formula. Okay, that is the correct. Now it is okay. Next term. Now like what we use, if we have this term del y upon del t, then we will directly substitute this term. Okay, now come to the next, the Laplace transform of del 2y over del t square. What is this? The Laplace transform is nothing but like dou over dou t and dou y over dou t. Okay, we can easily pronounce this del and dou also, because del types are like it is also del, it is also del, it is like also del. There are so many types of del, so like we are just we can just pronounce this dou. So this is the second order derivative, partial order derivative with respect to t. Then we can write this. And what is this? This is the like this is the like this thing, and I can write this is v. So the Laplace transform of dou v over dou t, and we know this formula. This formula is nothing but s v bar. Now the Laplace transform of v is equals to v bar. I am taking v bar xt minus like here v, and I'm just letting this v, considering this v. Okay, so v bar x minus this is nothing but v x 0. Now what is the value of v bar s? V bar s is nothing but again v bar s is nothing but the value, this is like del y by del t, so it is nothing but this thing. Again I am putting this here because that is the del y by del t, and Laplace transform of that del y by del t, it is nothing but Laplace transform. Na Laplace transform, it means I am putting this thing here. This thing is nothing but del dou Laplace transform of dou y by dou t, and it is nothing but s y bar x t minus y x 0 and minus what is this v is nothing but y dash, and I am just putting here y dash means del y over del t at x comma 0. Now it is nothing but s square y bar xt and s y x 0, and I can write this thing is a del t, del and subscript in subscript there is a t x 0. So this is the form, you can see here, this is the form. Okay, yt, it like the meaning of yt is nothing but the like partial derivative with respect to t. Now come to the next, now come to the third one. Third one is the Laplace transform of del y over dou y over dou x, It means the Laplace the derivative, partial derivative with respect to x. Now this is the respect to y, and these two terms are with respect to x. Okay, we have these four terms only, and we will substitute these four terms into the differential equation, and we'll get the ordinary differential equation. We will solve by using constant coefficient, by using in a linear differential equation, like whatever we will get, then we will solve the differential equation, and we will take a Laplace inverse by using this. Okay, now so by using the definition of Laplace transform, that is nothing but 0 to e to the power 0 to infinite e to the power minus st. Ft is nothing but del y over del x, and it is dt. Now here you can see integration with respect to, like here t is also here, t is also here, but there is no function of t rather than this. So I can just like by Leibniz rule, it is nothing but total derivative under the differentiation. Okay, it is this, like this the form. So what is this? This is the nothing but d by dx, and Laplace of y. What is the Laplace of y? It is nothing but y bar upon dx. I can write this thing, same thing. Now come to the fourth. What is the fourth? Fourth is the Laplace transform of d2y over dou 2y over dou x square. So now I can write this thing, Laplace transform dou over dou x and dou y over dou x. What is this? I am considering this is v. Okay, like Laplace transform of dou v over dou x, and what will be the value of this thing? This is the nothing but simple d by dx. So it is nothing but simple dy, like Laplace transform y bar dy bar over dx. Now here, what is the v? V is nothing but dou y by dou x. And what is the Laplace transform of this thing? This thing, the Laplace transform is nothing but this. Okay, by using this, okay, d2 they are like dy bar upon dx. Now you can substitute this term is here, so it is nothing but dy bar over dx square. So you can see here, this is the thing. Okay, so by using this, like these four terms, we will easily calculate the partial differential equation. Now come to the question and see the question, how can we solve this differential equation? Now we have this equation, and we have to calculate the solution by using Laplace transform. Like this equation is nothing but heat equation, like heat equation in a partial derivative function. So basically we have the derivative and some IVPs here, and now del u dou u over dou t, like dou u over dou t. Here is the dou u over dou t, like it is in a form y, and I'm just taking about u. So dou u over dou t, it is nothing but s. I am just replacing. So first of all, I am just taking the Laplace transform both side of the equation number one. This is nothing but equation number one. Here x is greater than 0, t is greater than 0 always. Okay, t is time and x is the the different, like the displacement or distance. Okay, now here x is greater than 0, and I'm taking like this, the Laplace transform of dou u over dou t, it is equals to Laplace transform of dou 2 u over dou x square. Now the Laplace transform of this is this as u bar. Okay, the Laplace transform of u is nothing but u bar. Okay, u bar x comma s minus u x comma 0. Okay, now is equals to k. It is, what is this? This is nothing but d2 y bar over dx square. Now here you will get the value of x this, so it is 0. So s bar x 0 is equals to k d2u over dx square. Now we have this del u s square. Okay, now this is the differential equation of the form of the constant coefficient. Like you can see, assume this del 2 u d2 u bar over dx square, or minus s upon k u bar x minus s is equals to 0. Okay, I can write also this thing u bar x minus x comma s. So it is nothing but a like a function, representation of function. Now this is the differential equation of constant coefficient, like d2 minus s by k and u bar x comma. This is the ordinary differential equation. So auxiliary equation by using the complete integration by using auxiliary equation, or there is this term, right hand side term is zero, homogeneous constant coefficient differential equation, only complementary function is the solution. Okay, auxiliary equation is nothing but m square minus s upon k is equals to 0, then m is equals to plus minus root of s by k. Then the solution is nothing but s bar. Solution of this differential equation is nothing but s bar x comma s is equals to a is a constant, or we can write like c1 is a constant, e to the power 1 root is s by x, s by k, plus c2 e to the power 1 root is minus, like 1 root is minus root of s by k, and we have to calculate this value. So now we have IVP. Like first thing is here, like calculate this. We have u x comma 0 is equals to 0 when x tending to, as x tending to infinite. You can see here x is greater than 0 means x tending to infinite. Or there is a thing, if I'm taking the Laplace of this function, if a function like remember this thing, if a function is tending to, if a function is equals to 0 as x tending to infinite, if I'm taking the Laplace transform of that function, that there is no chance that the Laplace transform of that function also tending to 0. So u bar x 0 is also 0 as x tending to infinite. Okay, so c1 equals to 0 here. Okay, I'm putting this IVP in this case, so c1 equals to 0. So now we have to talk about the C2 now. Basically we have u IVP, second IVP, this is the first IVP, second IVP is xt, is a function ft. Then if I am taking the Laplace transform of this thing is equal 0t. Okay, 0t, function 0t, or if I'm taking x equals to 0 here, x equals to 0, then u0t is equals to 0 to infinite e to the power minus st ft dt, or it is nothing but a, like the derivative of that function, like ft, Laplace transform ft, like I am taking just f bar t, that is the Laplace transform f bar t. Okay, so it will be the Laplace transform f bar t, and if I am taking x equals to 0 here, let me check it. If I am taking x equals to 0 here, okay, x0, then that is f bar s, the Laplace transform of this function is f bar s. Okay, like this is the term, u f t is 0 to infinite e to the power minus st ft dt, and it is nothing but f bar s. Laplace transform of this function is f bar s, and if I'm putting this term is here x0, if I'm putting x0, this term is 0, like u bar s x is equals to c1 e to the c2 e to the power minus root of sx by x. And if I'm putting x0 here, so y bar is nothing but, it is y bar, y bar is nothing but 0, s is equals to c2 e to the power 0, or it is nothing but c2. Okay, e power 0 is 1, and c2 is nothing but f bar s is equals to c2. Now I am putting the general solution here. So general solution is nothing but u bar x comma s is equals to c1 0, c1 totally 0, and now c2 is f bar s e to the power minus root of s by k x. If I am taking, now this is the solution, and now I am taking the inverse Laplace transform, taking inverse Laplace transform. So this will be the ux comma t. Okay, by taking the Laplace, by taking Laplace t, or this t will be s. Okay, this is the t, and I'm taking the Laplace transform of this at x equals to 0. So this will be the function ut, and it is nothing but Laplace transform f bar s e to the power minus root of k into x, or it is nothing but, okay, f bar s, or there is no function, specified function, there is only ft, or I can write this whole thing in ft, but yeah, of course, u x t, or this is the function e to the power minus root s by k, and it is the Laplace inverse of f bar s or also Laplace inverse, like I'm not taking in the multiplication. Oh yeah, you can write this is the term, because there is no specified function. If there is a function like sine x, cos x, sine 2x, sine ax, like ex, if there is a function, then we can easily solve this further, but there is no function is specified here, so we can easily solve this, like this, the solution of the heat equation. So main thing is here, using the IVP. Okay, this IVP, by using this IVP, C1 will be 0. If C1 will be 0, then using this IVP, if X is 0 here, then thing is here. And now on finding the Laplace transform, like there is a T converted into S and X is 0. This is nothing but Laplace transform, and this is the definition of Laplace transform. And now putting here s bar 0x, it is the Laplace transform, and by the solution C1 is already 0, so C1 is already 0 by using x equals to 0, because we are using x equals to 0 also here in this definition. So x equals to 0, and this is the condition. So C2 is nothing but f bar s, and now put here and taking the inverse Laplace. So what is the process? Process is the taking Laplace transform. First thing is here, second thing is here, solve the OD and find the solution, like whatever the OD, like constant coefficient, second order differential equation, linear differential equation, or like something like variable separable can be like maybe there. Okay, so and third thing is there, using IVP, finding the value of coefficient, and then fourth thing is here, important thing, like that is the important process or important step, that is like that is the taking the inverse Laplace transform. So this is all about the partial derivative of the partial differential equation by using the Laplace transform. So thanks for watching my video. Keep watching MS Maths, and if you just want to subscribe the channel, and you can subscribe, and you should subscribe the channel, and like the video, share the video, and support us. Thank you. Bye bye.